So, picture this. You grab a pen and a blank piece of paper, and you just scribble a totally random squiggly line. Now, imagine someone walks up and asks you to calculate the exact, precise area underneath that curving boundary. And I mean down to the absolute last decimal. There are no straight edges to work with, no simple rulers you can just lay down. It is literally an impossible, continuously curving shape. So how in the world do you do it? Well, that is the ultimate problem calculus tries to solve. And the specific tool we use to unlock it, it's nothing short of mathematical magic.
Hey everyone, welcome to The Explainer. I am beyond pumped to have you here today, because we are going to be demystifying one of the most powerful, game-changing concepts in all of mathematics, the definite integral. Look, if you've ever sat in a classroom, stared at a textbook, and felt completely intimidated by those weird, stretched-out S symbols on the whiteboard, honestly, don't sweat it. By the end of our time together, you're going to see exactly how this ingenious little tool lets us map out irregular shapes, track physical motion through time, and even calculate the infinite. All right, let's dive right into this.
Okay, here's our game plan for today. We'll kick things off with the formal definition, then reveal how integrals are often just basic geometric shapes in disguise. After that, we'll tackle the whole net versus total area debate, run through a quick toolkit of rules, and wrap up by learning how to find the average value of an infinite number of data points.
Let's start right at the beginning with Section 1, the definite integral defined.
You know, back in the day, before this tool was actually invented, mathematicians basically relied on Riemann sums to estimate area. They'd just pack a bunch of tiny rectangles under a curve and painstakingly add up all their areas. But those early methods came with some pretty strict mathematical handcuffs. The function had to be perfectly continuous, no breaks allowed, and it had to stay entirely above the x-axis, meaning every value had to be strictly positive. But let's be real, real-world problems just don't play by those rigid rules, do they? Data fluctuates, signals randomly drop, values dip into the negatives all the time. So the definite integral arrives as this monumental, much-needed upgrade. It totally generalizes the concept of area under a curve and lifts those strict requirements, which frees us up to analyze a much broader, wilder set of messy, real-world functions.
Let's break down this beautiful notation piece by piece, so it literally never intimidates you again. This specific layout actually goes all the way back to the late 17th century, cooked up by the brilliant mathematician Gottfried Wilhelm Leibniz. First up, think about that big, elongated S shape. That symbol simply stands for the word sum, representing the summation of infinite slices of area. Just above and below that S, you'll find the lower limit, called A, and the upper limit, called B. These limits of integration are absolutely crucial. They tell us the exact, specific boundaries we're looking at on the x-axis. Inside those bounds sits the integrand. That's really just the function itself, the actual curve we're evaluating. And finally, tacked onto the very end is the dx. This tells us our variable of integration. And honestly, it's just a dummy variable. You could swap it out for a dt or a du right now, and the actual area computation would stay exactly the same.
Moving right along to Section 2, integrals as geometric shapes.
I'm going to let you in on a little insider secret about evaluating these expressions. Calculating integrals by taking the limits of Riemann sums step by step, it is incredibly tedious. The algebra explodes and the math gets super heavy really fast. But because we know a definite integral just represents the physical area under a curve, we can often completely bypass the complex calculus entirely. Seriously. Before we touch any heavy algebra, we can often just anchor these symbols to familiar geometric shapes that we already know how to measure.
This is a perfect example of what I mean. If you were handed a test and asked to evaluate the integral from 3 to 6 of the square root of 9 minus the quantity x minus 3 squared, your first instinct is probably pure panic, right? It looks terrifying. But take a deep breath and just picture the graph of that function. That scary-looking square root equation actually describes a simple, perfect semicircle resting right on the x-axis with a radius of exactly 3. Plus, our limits of integration only ask us to measure from 3 to 6, which is just the right half of that semicircle. So we're really just looking at exactly 1/4 of a full circle. Instead of doing brutal calculus, we just use the standard everyday geometry formula for the area of a circle. We take 1/4 times pi times 3 squared. We get 9 pi over 4. Boom, done.
We can totally apply this same visual shortcut to straight lines too. Think about a simple linear equation like f of x equals 2x over the interval -3 to +3. Instead of running a complex algebraic integration, just think about the shapes. This straight diagonal line basically just forms two perfect triangles against the x-axis, one pointing up and one pointing down. And since we all know the classic geometric formula for a triangle, 1/2 base times height, we can easily calculate the area of the top triangle, which is 9, and the bottom triangle, which is also 9.
entirely without breaking a sweat. It's literally just geometry. But wait, what exactly happens when that graph dips below the x-axis, like that bottom triangle?
That brings us right to Section 3, net versus total area.
All right, the absolutely crucial thing to grasp here is the difference between net signed area and total area. When a function dips below the horizontal x-axis, the physical area calculated between the curve and the axis is mathematically considered negative. Net signed area adds the positive area above the axis and explicitly subtracts the negative area below it. If those two physical areas are identical in size, just like our two triangles from a minute ago, your net signed area is exactly 0. Total area, on the other hand, just wants to know the physical amount of space, completely regardless of its orientation on the graph. To find that, we use absolute values to mathematically flip the negative area upward, treating every single boundary as a positive value.
Let's ground this in a really intuitive physics analogy. One of the single best real-world applications of integrals is finding your total displacement when you only have your velocity over a certain period of time. So imagine you jump in a car and drive straight away from your house at a constant speed of 70 miles per hour for exactly 2 hours. If we graph your speed over time, this forms a perfect flat rectangle. The area of that rectangle is your speed times your time, 70 times 2, giving you an area of 140. In the real world, that geometric area literally is your physical distance. You are exactly 140 miles away from where you started.
But let's complicate the road trip slightly. Say you drive straight north at 60 miles per hour for 2 hours. The area of that rectangle means you're 120 miles north of home. That's a nice positive area sitting above the x-axis. But then, you realize you forgot your wallet. So you turn the car around and drive back south at 40 miles per hour for 3 hours. Driving south is a negative velocity, so that draws a new rectangle with an area of 120 miles completely below the axis. Your displacement, which just means how far you currently are from your original starting point, is 120 minus 120. Those two areas perfectly cancel each other out, leaving a net signed area of exactly 0. You are right back in your driveway.
But hey, what if you don't actually care about displacement? What if you're a mechanic looking at the car's odometer and you just want to know the total area traveled, completely regardless of the direction you drove? I mean, the car still burned gas, right? The tires still experienced wear and tear. You drove 120 miles out and you drove 120 miles back. In this specific case, to find the true total area, we mathematically place absolute value bars around the function. This forces that southern drive to be treated as a positive distance. Now we just add them up, finding a total area traveled of 240 miles. Makes sense, right?
Let's quickly move into Section 4, Rules and Properties. Okay, rapid fire time. To help you evaluate complex integrals without having to graph them out every single time, here is an essential toolkit of core properties. First up, if your upper and lower limits of integration are exactly the same number, like measuring from 5 to 5, the integral is just a vertical line. It has 0 width, so it contains absolutely 0 area. Second, if you ever need to reverse your limits of integration, like flipping the a and b positions, you can totally do that. You just have to slap a negative sign in front of the integral to balance the equation. Third, the integral of a sum is simply the sum of the individual integrals. This is a massive lifesaver, because it means you can take a huge, terrifying algebraic equation and break it apart into small, bite-sized chunks. And finally, if there's a constant multiplier sitting inside your function, you are completely allowed to pull it right out to the front of the integral sign, compute the area first, and then just multiply it back in at the very end.
And finally, Section 5, Finding the Average Value.
For our final stretch, let's zoom out and see how this amazing mathematical tool builds off something you do all the time. Think about how you traditionally calculate a test average. If you get 6 discrete, individual test scores over a semester, say an 89, 90, 56, 78, 100, and a 69, you simply add those 6 numbers up to get a total of 482. Then, you divide that total by 6. You get an average of 80.33. That's a solid B-. It's incredibly straightforward arithmetic.
But here's where it just completely breaks your brain a little bit. Suppose a function doesn't give you just 6 nice discrete numbers. Instead, it gives you the continuously changing speed of an object moving over time. And you need to find the object's average speed. The core problem here is that speed isn't a discrete set of numbers you can count on your fingers. It's a smooth, unbroken curve. A continuous function literally takes on an infinite number of values over a given interval of time. I'm talking infinite fractions of a second to account for. So how in the world do you add up infinity and divide it?
Well, spoiler alert, you use the definite integral.
The exact, precise average value of a continuous function over the interval a to b is simply the definite integral of that function evaluated from a to b, all multiplied by a simple fraction, 1 divided by b minus a. The definite integral acts as our ultimate infinite sum. It seamlessly gathers up the total accumulated area of all those countless, completely unmeasurable data points. Then, that simple fraction in the front basically divides that massive total sum by the physical width of the time interval itself. By substituting discrete addition with continuous area, it elegantly and perfectly solves the seemingly impossible problem of averaging infinity. And that pretty much brings us to the end of our journey today. We've seen how the definite integral takes the incredibly simple concept of counting the area of a shape and stretches it to map out irregular geometric boundaries, logically track physical displacement through time, and seamlessly average out infinite points of flowing data. It really makes you wonder, doesn't it? If a single, elegant mathematical tool can do all of that just by measuring the space under a curve, what other invisible forces and hidden truths in the universe could integrals help you reveal? Keep exploring, keep questioning everything around you, and I will see you in the next explainer.